evening, everyone. Welcome back to the another departmental webinar. Today's speaker is Professor Gopal Dixit, and Professor Dixit is an assistant professor at Department of Physics at IIT Bombay. He did his MSc from University of Allahabad in 2004, and he did his PhD from IIT Kharagpur in 2011. So he is a guest scientist in a couple of places. One is in Technical University Munich, Germany. Another one is Arnold Sommerfeld Center for Theoretical Physics, Ludwig Maximilians University, Germany. And he conducted his postdoctoral studies in a couple of places. One is in Center for Free Electron Laser Science to take electron synchrotron, Hamburg, Germany, from 2011 to 2013. And another postdoctoral study conducted in Max Born Institute for Nonlinear Optics and Short Pulse Spectroscopy, Berlin, Germany, from 2013 to 2015, before he joined at IIT Bombay. So he has several awards and recognitions on his name, and some of the recent ones are: he received Ramanujan Fellowship from DST, and also received Max Planck India Visiting Fellowship, DAD Research Ambassador Award. He's also received Early Career Research Award from SCRP, and he's also a member of several bodies, American Physical Society as well as Royal Society of Chemistry. He is a member of Indian Society of Atomic and Molecular Physics, and his primary area of interest is research group works on probing ultra-fast processes in nature, imaging electrons at attosecond and femtosecond time scales. And today he is going to talk to us about the instances of bond breaking and bond making during chemical reaction. Professor Dixit. May I request everyone to mute themselves, please?
Thank you very much for your kind introduction and accommodating me in your departmental webinar. Today I'm going to discuss some of the very recent and interesting works that we are doing. So the title is like you would like to make movies of chemical reactions where chemistry is taking place in real space and in real time. But before I will go to talk about chemical reactions and microscopic processes, the first thing I would like to present is how people have thought to take a picture of the microscopic processes. So this is a very old picture of Myobris around the end of 19th century. And there was a question at that time that whether this galloping horse during this race have any time completely in the air or not. And Myobris took this question as a challenge, and then he built up a flash photography. This was somewhere near to Stanford, and it has a very interesting relation. I will show why it is in my talk. So this is the paper that he wrote down, The Horse in Motion, and you can see that indeed there are some instances when all the four legs of the horse is in the air. So this is, we are talking about the microscopic things. Now let me ask how you take the picture of the microscopic object, like how the atoms are arranged in a molecule or in a solid, what is the structure of your protein or DNA and all these things. And the answer could be given by this big machine. This is a picture of a synchrotron, which we call as a third generation X-ray source. And X-ray diffraction has been proven to be a very powerful method to obtain the real space images of the constituents of the matter. This is the big Petra ring, which generates a very intense X-rays. I will come the properties and the details in a minute. And this used to be my office during 2011 to 2013. This is a Center for Free Electron Laser Science. And the whole, let's say the important role of the X-ray diffraction is getting the structure. And here I have taken this slide from internet, and you take the X-ray from this big machine and you shine onto this crystal. This crystal will diffract the X-ray beam. So you will get the some X-ray diffraction signal, perform some kind of algorithm to get the phases and all these things, and you can get the structure. And these are the different kind of biomolecule structures. And so crystallography has been the main method to get the structure of all biological as well as the solid state samples. And I don't know how much this is true, but at least this website says that there are around 28 Nobel Prizes for the crystallography or X-ray crystallography. However, there are some serious problems, and there are ways to overcome it, but there is no unique way. So one of the problem is the radiation damage. So what people generally do is that they put the crystal into some kind of coolant to avoid the radiation damage. And the work that was proposed in 2000 by Richard Nietzsche and Jonas Haidu and other people, that they suggested that instead of having synchrotron radiation, which is around nanosecond long pulse, it's quite long radiation in terms of the time. If we can have some very, very short pulses of X-ray, we can avoid radiation damage. So this is the picture, and this is the molecular dynamic simulation of this T4 lysozyme, which was exposed to X-ray of intensity 10 to power 12 watt per centimeter square. With energy 12 keV, because 12 keV will give you 1 angstrom spatial resolution. And as you can see that at 5 femtosecond, this molecule is completely intact. There are some atoms are coming out. Up to 10 femtosecond it is intact, and after that it is completely fragmented. So if you have a large pulse, large radiation or large flashes of X-ray radiation, then what happens that the signal that you are getting from the X-ray diffraction is not actually coming out from this intact or the original sample, but it's more like a diffracted sample. So what people wanted to do always is to do what is called diffraction before destroy. And this is the simulation with, I think, 2 femtosecond long pulses of X-ray. And then they have done for different pulses. And this is for the 10 femtosecond, and this is for the 50 femtosecond. And 50 femtosecond immediately tells you that everything is completely blasted. You can compare. This is also 50 femtosecond after the pulse has interacted with the same molecule, and this one. And you can see as the pulse is become longer and longer, your molecules, your atoms within this biological sample is start flying away. So this is the one problem. Remember, this paper came in 2000, and at least when I talked to the authors of this paper, and whenever they used to present this work, people always thought that this is kind of some sci-fi movie, because they thought that having a 5 femtosecond or 2 femtosecond X-ray pulse is not going to be possible at all. This is the one challenge that the synchrotron sources were facing or is still facing. The other important challenge that where is till, let's say, the 20th century, the whole idea was that, okay, structure function relations is the ultimate goal. So once you have the structure of a molecule, you can get the you can deduce what could be the functionality. And this was, let's say, the when you got the structure of the of the DNA and RNA and other thing. And this was, I would say, a kind of very powerful but static view of matter. Now the things have changed. What we need actually is a dynamic picture, because the nature is dynamic. And this is the new aim of this 21st century, that nature is moving, and there are so many processes, sometimes competing processes, and static view is not going to be sufficient. So we really need a dynamic view of nature. I mean, when I would say nature, means how these biological molecules are performing, are doing their actions. For example, the cis trans isomerization of your retinal protein, which is the key for your vision and all kind of things. I will come to few of the questions later. So not very surprisingly, in 2009, the first X-ray free electron laser came into existence in USA, the same place in California, where this Myobridge was making a flash photography of your moving horse. So XFEL stands for X-ray free electron laser. And here is your energy, and y-axis is your Prig billions, the like number of photons per pulse per unit area. And these are your standard synchrotron. So this is the BASI, this is the Petra 3, this is the ESRF, this is the APS in Chicago, this is the Spring 8 in Japan. And this is where your LCLS, which is the first XFEL in hard X-ray regime. So you can see that there is almost 10 orders of magnitude enhancement in the Prig billions, which is very important because the Prig billions is going to decide how intense is you're going to be the scattering signal or diffraction signal. Not only that, they can produce the pulse duration into femtosecond or some femtosecond duration. And I would not say what is the meaning useful of the X-ray, because I believe that all of you know why the X-rays are so useful and all these things. There is an alternate way to produce X-ray. Of course, not the hard X-ray, but you can go to soft X-ray regime. It is based on the high harmonic radiation, which I will not discuss in this talk at all, but we are also working into this direction. So where are these XFEL till date? So these are the 5 XFELs operational. The first one in LCLS USA, and you can see that this is a linear accelerator. So this is around 2.5 kilometer undulator, and then they take care about all the beam optics and everything, and these are the experimental halls. And immediately Japanese came and started their XFEL in the same place where this Spring 8 is there. So this is, I think, Spring 8. This is your Sakla. European XFEL came into existence 2016-17. Now Swiss FEL in the same place where you have a PSI synchrotron, and this is the PAL XFEL in Korea. And so this is the word map of all the XFELs I have talked about. And the newer version of XFEL, which is in Germany, Hamburg, where I was working, is somehow much better because they have a higher rep rate. Okay, this is a technical term, you could ignore it. This is the inside view of your European XFEL. This is a long tunnel, and these are the superconducting coils where your X-ray radiation is going to be passed through. And what people thought in 2017 that your European XFEL will allow you to watch movies of the molecule in action. So this is the one thing. And as I told you that this LCLS in USA came in 2009. And after some commissioning experiment, this is the first experiment carried out by the Henry Chapman from our institute in CFL, that protein X-ray crystallography of nano crystal. So you don't need to grow any more micro size or even bigger size crystals, but you can have even a smaller crystal, and you can obtain a meaningful structure of your protein. I don't will go into detail what is all this about, but just to show this thing. Not only this X-ray sources allow you to have a structure of a small nanocrystals, but also they will also allow you to get the structure of those proteins or those biomolecules which are very difficult to crystallize. I mean, people spend their whole PhD to get a crystal of one biomolecule. There are a lot of floppy proteins, so they are hard to crystallize. So what they do what is called a single molecular imaging. So they will send the molecules from this liquid jet, and every time this X-ray will see a different orientation of your floppy protein, and they will collect hundreds of thousands of signals, and then there is a well-established algorithm which will try to get the orientation and all these things, and then you can get the let's say the structure of your floppy protein. One of the key thing in this X-ray crystallography or X-ray diffraction is this equation. This equation is that intensity at the detector is nothing but a square of the form factor, and form factor is the Fourier transform of your electronic density. So this is the square of the electronic density, Fourier transform of the electronic density. Of course, when this machine started working in 2009, and after that in Sakla, people immediately thought, oh wow, let's look some chemical reactions, because we can have X-ray diffraction into pump probe configuration, where our pump will induce a reaction, and then X-ray diffraction will be used as a probe. And at every pump probe delay time, you will have a diffraction signal, and then you can record them. And this, okay, so, but this created a problem, and I will discuss what is the problem, is as follow. Whenever you talk about any chemical reaction, only very few electrons are participating in your reaction, and most of the electrons are static. For example, if you say, let's say the benzene and this charge migration or double bond migration happens, it's a 1 electron per carbon atom is moving, and rest of the 5 electrons are static. Not only that, the core electrons, which are very tightly bound electrons, think about if you have very tightly bound anything and you try to scatter something, this will be scattered more. The valence electrons are very diffuse in nature and very loosely bound, so they will scatter very least. So people immediately posed a question to this chemical community that within the signal to noise ratio, watching the X-sun driven by 1 electron out of hundreds and thousands of electrons, you are not going to see anything. So forget about making a molecular movie. Another aspect I would like to bring into your notice about the power of X-ray crystallography is as follow. This is the slide taken from Alan Orwell from Diamond Light Source UK. They are also building XFEL there. And this is the years, and this is the how many structures you have obtained from X-ray, and how many structures you have obtained from electron microscopy. And no doubt that X-ray dominates much higher than this one. And this is the latest number. I got it from PTB data bank, and you can see that even the cryo electron microscopy is not going to touch anywhere what is X-ray crystallography is doing. And not only in this one, but we are living into this COVID era, and this is the global structure biology response to COVID-19. And you can see that most of the cryo samples are done at 100K Kelvin, only 47, whereas the X-ray crystallography is around 250, and they are into a different temperature range, and they have even better resolution, so they can have almost like a 1 angstrom, and as far as larger, around 4 angstrom. So no doubt X-ray crystallography or X-ray diffraction is much more powerful than let's say the cryo-EM, which is maybe a method of choice for some of you to get the structure of any biological sample. which is not the talk of my present one, but what I'm going to talk about how to really image this chemically active valence electron, which I was talking about. So I will take a couple of chemical reactions into consideration, but before, at least I would like to give you a time scale which I'm going to talk about. So this is the graph, and this is the length scale. And if you see this leftmost corner, you can see this is the attosecond and picometer where electrons are moving within the atom. And as you move away from this corner, this is the femtosecond when electrons within the molecules are moving. So they are participating in vibrational motion. And as you go longer, they will be participating into rotational motion. And the length scale is somewhere in angstrom. So the first equation I'm going to discuss is degenerate Cope rearrangement in semi-billowing. I'm not a chemist. I'm not the expert of this chemical reaction. Of course, that time we had a postdoc who was a chemist, and he was helping us to understand this chemical reaction. I learned that this is a very textbook chemical reaction for pericyclic people. So, and people like Ronald Hoffman and all the people have studied this reaction into great detail. So what is the question in this reaction is as follow. So this is the semi-billowing. You can think like a benzene if you are not a chemist. And you see that when the reaction is going over the barrier, these are the electrons are moving back and forth. So these are your Lewis structure. This is some kind of proposed reaction intermediate, and then the whole double bond might break this one. So this is the reactant, this is the product. And when it is going to the tunneling, of course, the reactant and the product are same for both the channels. However, there was one basic question which I believe it is still there, and there are several ways to answer this one. All are very indirect ways. When the reaction is synchronous and when the reaction is asynchronous, means whether the bond breaking and bond formations are taking place at the same time. So this is what we call as synchronous or in phase. And when the bond breaking and bond formation are taking at two different times, means first the bond is broken and then the bond is formed. This is called unsynchronous or stepwise or out of phase. I mean, there are so many technical terms. To initiate such kind of chemical reactions, there are some schemes like down-chip, pump dump, or photoimpulsive methods. So this reaction is driven by the ground electronic state. The excited electronic states are not participating in this one, and this is the effective reaction coordinate computed using quantum chemistry method. We have also done the nuclear dynamics on that. I will show you the results. And for this particular molecule, around 1972, people have got the static structure of semi-billowing using the electron diffraction in gas phase. So what people have done, this is a very, theoretical point of view, and I'm also a theoretician. Let me make a disclaimer at this point of time that all the results I'm going to show you are based on the theoretical modeling. Okay, and don't get confused at the end of the talk that I have done some kind of experiments. So what people have done, so for example, let's say the carbon. So what they did, they just partitioned the total electron density into two pieces. The 2 electron corresponds to the core electrons, and the rest of the 4 electrons corresponds to the valence electrons. And now out of the 4 electrons, again they have partitioned, and the 3 they have attributed to the other valence electrons, and 1 electron they have assigned to what is called pericyclic electron. And they have analyzed this pericyclic electron density. So this is the results from Jörg Munch from Berlin. The paper came in 2011 in Electron Chemistry, and what is plotted in this figure is rho peri. And when the reaction is going via tunneling, you can see that there is no bond here. This bond is intact as the reaction is proceeding. The bond is broken now. You can see that there's a very minimum electron density at this point of time, and the bond is also formed. and so on, and then you get the product. When the reaction is going over the barrier, same as previously, but here the bond is broken. However, the new bond is not formed. And this kind of analysis, I would say, is kind of routinely employed to answer the questions like the tunneling is asynchronous and the over the barrier reaction is asynchronous or stepwise reaction. And as I said, that this is a very, very artificial and ad hoc way to answer it. Nature does not know to separate this kind of electrons. So this was the challenge. So we took this challenge and we thought, okay, let's try to address from the time resolved X-ray diffraction point of view, and this will help maybe this chemical dynamics community a lot. So what is the first question we thought to address?
Can I ask a question?
Yes, sure.
Yeah, so in this, the picture above, the single bond that migrates from left to right, there is an asymmetry because there are double bonds between 3, 4 and 7, 6.
So there is a double bond 3, 4, 7, 6. And this is only a planar view of this molecule. This is a non-planar molecule.
Yeah, I meant if this single bond which shifts the 2, 8 goes over to 4, 6. Is that right?
2, 8 to 4, 6, yes.
Then there is actually an asymmetry because there are double bonds on the 4, 6 corners, whereas there were not on the other side. So, I mean, how can one actually tell that this has moved? It's not actually a symmetric situation to start with.
It's not, but what at least, I mean, maybe somebody could comment if I'm wrong. Whenever they have, let's say, the chemical reaction, one could say that they have always the mixture. So it's very difficult to say.
All right, just a curiosity. It's okay, you carry on.
Yeah. So
Gopal,
okay.
I have a question. Can I ask?
Yes. Yes.
Yeah. Maybe you can tell what is your reaction coordinate?
Okay. Reaction coordinate, of course, if you,
in this case.
Yeah, in this case, what has been done is they have defined a reaction coordinate based on the bond length difference between 4, 6 minus 2, 8. And that's what we define as a effective reaction coordinate. Because the full quantum dynamics for this molecule is beyond the scope. What we have calibrated this one with this IRC simulation, and the results are identical, I would say.
Gopal,
You got the answer?
Other way maybe. It's 2, 8 minus 4, 6. No? It's negative on your left.
No. So what
Starts from negative value, you see?
No. What we are saying that, so this bond supposed to shrink and this bond supposed to elongate.
Yeah. So I'm saying, is it because your minima is at -2, value is -2, your xi value. So when you start with the xi value which is negative. So it has to be something minus something which is negative. So
Okay.
maybe 2, 8 minus 4, 6.
Okay, 2, 8 minus 4, 6. Okay, other way around. Yeah.
Yes, and now that is what is happening. Yeah.
Okay.
Thank you.
Gopal, this is Sunoj.
Yeah.
Just to follow up on the reaction coordinate, do you have a clarity on the width of this profile, that what you're showing as tunneling through the green arrow? So it would drastically depend on the width. So is there a clarity on the width, or this is just purely qualitative?
No, this is the computed reaction coordinate.
So what is the width, which would be a critical parameter to see whether there is a chance of tunneling, right? If you use Wigner correction and things like that. So
the tunneling, I mean, I have not shown here, but maybe we can discuss later. We have modeled it based on Gaussian wave packet. So in the beginning, what we have done, okay, let's say the 100%, so 50-50, and then slowly it start getting the weightage over other direction.
Okay. So one more comment is that you said that quantum dynamics, of course, it depends on the extent of sophistication, but I think this would be amenable for metadynamics, where you can, because the moment you described this 2.8 and 4.6, it reminded me of collective variables in metadynamics. So you could do a constrained metadynamics that will perhaps give you some interesting insights.
Okay. Okay. Yeah,
Okay.
that's true. That's true.
And at the end of the talk, I will send you 2 references on semi-Bulvelin, where there people, particularly Paul Schleyer, who is a pioneer in molecular orbital theory, he had studied effect of alkali metal ions in making this process entirely barrierless.
Okay. Okay.
That is.
Is some person from UK?
No. He was in Princeton, Germany, and eventually in University of Georgia before he died.
Okay. Okay.
So he had studied effect of lithium plus in making it a barrierless process.
Okay.
This COP rearrangement in semi-Bulvelin. I have the paper with me.
Okay. Okay.
And another point input from chemistry domain is that people have studied heavy atom tunneling. So here you are probably referring to a carbon tunneling.
Carbon tunneling, yeah.
Right.
Yeah.
So Westborden, during his late phase of his career, he had done heavy atom tunneling on other type of system. That also I will send you the reference.
Okay.
Okay. Thank you.
So what we did, we thought, okay, let's do the complete time resolved X-ray diffraction simulation for this chemical reaction. And I will not go to the this big equation because this contains the nuclear wave packet and the electron density, intensity, and all these things. I will ignore it. But let's focus on the diffraction pattern. And these are taken a snapshot for 5 different times. 0 means the reactant and T means your product. And you see when the reaction is taking place via tunneling, a very careful observation tells you that indeed the intensity is decreasing at this point. You see this blue color, and slowly this blue color is diminishing, and then you have a less signal at this point, and then again you regain it. Okay. However, when the reaction is taking place via over the barrier, again you start getting a green color, so it means intensity is increasing. It reaches to the maxima, and then again it reduces. So it means that there are 2 different ways the reaction is happening, and this time resolved X-ray diffraction is capable to distinguish the 2 reaction paths. So this was I would say the first success for us, that okay, the time resolved X-ray diffraction is sensitive to this kind of processes. Then what we did, we just subtracted the one signal over the other and to see where are the maximum differences. So this is the results that scattering signal difference between over the barrier and tunneling. So of course the reactant are identical, so you're supposed to get a 0, and then you see the meaningful changes at large Q value, large momentum transfer range, and this maximizes, and then at T you supposed not to get, you're supposed to get a 0, but you see some ringing effect, and these ringing effects are due to the wave packet dispersion when the reaction is taking place over the barrier, when the your wave packet is dispersed, whereas in the tunneling your wave packet is not dispersed. So this is this, but it's not going to tell you anything about the reaction mechanism, but we wanted to understand and follow this Awanti Kemi 2011 paper. So what we did, we subtracted the signal at 0 for the following subsequent time. No, first we thought, okay, let's take invert the whole diffraction signal and get the electron density. So here is the tunneling, and these green dots are your core electrons, and these red is the diffused valence electrons, so-called. And when it is going to the tunneling, you see that at half point you just get splitting some kind of thing. So you can say that now it's 50-50 weightage from both the side, whereas in the over the barrier, not very meaningful changes. So total electron density is not going to talk about anything bond making, bond breaking. Then we subtracted, as I told you, from the subsequent. So in this signal, or in this result, T is equal to 0, signal is subtracted. and you see some spot here and there, and nothing is being. So we thought, okay, what is happening? We don't know about the bonding in antibonding. So let me come back again. And now what I'm going to tell you is very intuitive way, which is correct. So as I told in the beginning that your core electrons are intact, so they will be scattered more. It means that they will show into a large momentum regime, whereas your valence electrons are diffused in real space. So they're supposed to show their contributions into the low momentum regime. Of course, this is not a correct or strict way to define their contributions, because we know that at momentum transfer 0, all the electrons are contributing and it contains the total number of electrons square. So what we thought, instead of looking the full diffraction pattern, just small slices and increase the size of the slices and see what we are getting. So we took a small piece of slices and again perform the phase retrieval and got this electron density so-called. And this looks colorful, but maybe not a meaningful. Of course, it is a little bit different what we have seen the total electron density. But let me compare with this pericyclic electron density. We got the data from Jorgman and we have plotted in our color bar. And you can see that at this point of time, they have one-to-one mapping. Here again, and here they have the same when it is happening over the tunnel. Just let me remind you, these ringing effects, what you are seeing here, these are the artifacts of our rigid square edge filter function. So what we did in this one, we just put a rigid square filter function, and when you are performing the back Fourier transform during phase retrieval, these rigid edges are giving you a ringing effect. So this is the tunneling, and when we are looking over the barrier, it is one-to-one match. And here, remember, we are not doing any hand picking electron density. So we simulated the full diffraction pattern, which contains all the information. We can get the total electron density, as well as we can also get the so-called chemically active electron density, which is going to help us to understand bond making and bond breaking. And indeed, one case it is showing that one path is unsynchronous, and another case it is showing that the path is synchronous. Now one can ask the following question, that how robust is your method? I mean, what will be the size of your box which you are applying to total diffraction signal? We have tested for quite long range, and it is kind of robust. So let me quickly go to some other topic. So this is the old work, actually 2014 we have published into Nature.com. And I mean, one thing I would like to mention that in 2013, people like Sol Mukamel applied our method. They gave 2 different names. And what they look into this ring opening reaction of cyclohexadiene, and everything is perfect. They can answer several interesting questions. I'm not going to discuss their work, but let me come to another reaction which we have done very recently, surface diffusion. So this is the effective reaction coordinate. What I have taken the magnesium oxide 001 surface. So and the copper dimer is doing tumbling motion. In the beginning, it has a perpendicular configuration, and at midpoint, it comes to this one, and then again, it comes to this one. The question is that, can we understand the bond breaking, bond making in this reaction? Remember, people have kind of commented that you are talking about the carbon molecule content chemical reaction. So most of the electrons are valence. So then you are able to extract the this so-called chemical electron density. However, this is not anymore true for this one. So this is the diffraction pattern, again the total, and these are the total electron density. If you again focus little bit, you see these stripes, and slowly this will turn out to be like a black peaks because you have a periodicity. And as the tumbling motion is going, you see the inclinedness of these stripes, and then it comes out to the perpendicular. Okay, during the half time, and then again it will rotate like back and it will come back to this one. So the first thing we have answered that, okay, from this stripe orientation, you can get the orientation of this copper dimer over this manganese oxide. Manganese is this one, where the electron densities are is spherical. These are oxygen, which is so like more diffuse, and these are the copper dimer. Now what we did, one more thing, I mean, those who are crystallographer, they know that something is called Friedel's law, which tells you that your diffraction pattern is supposed to be centrosymmetric. F of q and f of minus q will give you modulus of f of q square, which is violated in this case, because this is also a signature of defects. Whenever you have a defect, you will see that the Friedel's law is violated. So what we did again, now this time we have taken a Gaussian filter, and this is the electron density, completely different. And here we can see that in the magnesium, these are your oxygen, and they have some kind of polarization. And slowly we see that when the bond is broken and when the bond, so between magnesium and oxygen, this bond and this polarization bond. So we do understand this thing. I mean, we did equivalent Bader charge analysis. I will not present this one, but in just 10 minutes, I will tell you how the standard textbook knowledge get completely misquoted when you go to the time resolved X-ray diffraction. So till now, everything I have talked about ground state, ground electronic state driven chemical processes or surface diffusion. What about when you have a coherent electronic motion, and what are the challenges? So around 2005 or 2007, people started thinking, oh, once we have these very ultra-short pulses, we can even see, let's say, the very fast electronic processes without getting contaminated by the nuclear dynamics, which are happening in femtosecond time scale. And this is the results from 2009, our review of modern physics paper. What they have done as a showcase, these are again a simulation. They took that 1s2p coherent superposition in hydrogen atom. And so you see, this is the charge distribution, the maximum here. As the time progresses, the charge distribution moves from upward, and it reaches to the maximum. And once it reaches to the maximum, it start coming to the downwards. And what people thought, from static to the time domain, just assign a t to the total expression, and then the everything is done. However, if you see the corresponding diffraction signals, when the electronic charge distribution is moving upward or when it is moving downward, diffraction signals are identical. So they do not have any notion of current or the direction, and they are going to give you a wrong time period. So the diffraction signal start repeating at half time, whereas the actual time period is double the half period. This is for the X-ray diffraction, okay? The same thing happened for the electron diffraction. So this is a paper from 2010 PRL from Tony Starres, Nebraska. They have took H2 plus, and they have created a wave packet between the gerade and ungerade electronic state, and you have a localization versus delocalization kind of charge motion, electronic motion. And at half time, when the electron is moving from left to right or right to left, they have the same signal. So they do not have the direction. Again, wrong. This is a 2011 paper where they did the double slit experiment in H2 plus, and in this case also they have the wrong thing. And so this was a problem in the community, and people were keep publishing. I came into this picture into 2011, and what we thought, okay, let's look everything from scratch. So to demonstrate the theory, I again took hydrogen, pump pulse, created the superposition of 3D and 4F. 3D and 4F have nothing to do. It's just for one very beautiful picture, nothing else. But the theory is very general. We created a wave packet, and you could think of that this plus and this plus or this same phase will create a maximum charge distribution. and these opposite phases will create a minimum charge distribution. So this will create a wave packet, and this will oscillate in a time, and at different time interval you bring the X-ray pulses and you create a diffraction pattern, and by varying the pump probe delay time you can make a movie of this diffraction pattern, and then you can make a movie of your charge distribution. What we did in this paper in PNS 2012, we did the full QED calculation, quantum electrodynamics calculation. And what we have shown in this case, so this is the electronic charge distribution at different times during the motion. You see that the charge distribution is maximum as the time progresses. It starts moving downwards, it reaches to the maximum, then it starts moving upward. This is the diffraction pattern obtained from the full QED. These are the momentum space, these are the real space. When it is moving downward, signal moves upward. When this is moving upward, signal moves downward. So indeed, it has a correct notion of the dynamics, whereas the standard one, which we just wanted to repeat, has again the wrong periodicity. Just a side remark, we can discuss a little bit later. What we have shown in this case, analytically, by doing the two ways, that if you do a semi-classical description of this time resolved X-ray diffraction, where the light is used as a classically or wave nature, and another case QED, the classical notion of light is not capable to capture this motion correctly. This is a very important, because generally people talk about quantumness of light using the G2 and all these things. I mean, a second order correlation function and less than one and all these things, but this is a much cleaner approach. Once we have established this one, this is my last slide, I hope. It was established that it is a current, and a lot of people compute this current, because following this equation of continuity, once your charge distribution of time dependent, you can also compute the fluxes. So we took a benzene and we created a coherent superposition in benzene, and then we created this arrows, which is nothing but current densities. And this we have shown. I mean, I will not go into this one because time is almost getting over. This is the work we have done this year, where we have proposed that, okay, electronic fluxes can be indeed probed by the time resolved X-ray diffraction. With that, let me conclude that it's really interesting. We are doing some other kinds of work, like one of my group member is doing charge migration and probing the fluxes in chiral molecules. Hopefully in future we will get more interesting. Little bit advertisement. We are organizing a Faraday discussion on this time resolved imaging. This meeting is in now online mode, so anybody can register and attend this one. There are a lot of interesting people who are going to talk about different aspects of ultra-fast processes in nature. I mean, for the chemist, one very important thing that they used to do over the years is called atoms in molecules theory. And this is the one which is giving kind of insight over the years to know where are the bondings and other things, thanks to Richard Bader. In this work, we have proposed, of course, the Bader theory is pure hypothetical theory. In this work, we have shown that the signal is nothing but apart from bunch of prefactor, Laplacian of the projected electron density, and Laplacian of your electron density is nothing but a Bader theory. So we have connected to the Bader, and this is nothing but Fresnel's diffraction in a technical term. And when we published our first paper in 2011, it was a huge success. We got even what you call NCB, this news channel NBC News in USA, even MIT Technological Report quoted our paper with this last line, that hydrogen atom will be just the start. It won't be long before we have videos of quantum motion of electrons in more complex molecules, perhaps even in biomolecules itself. With that, let me thank you very much. The flux work was done by Gunter and Vincent. They visited me for 2 months from the group of J.C. Tramley, and the surface diffusion work was done by Kai Topper, who also visited me last year for almost like 1.5 months, and who wrote the code and everything. Thank you very much for your kind attention. Thank you.
Thank you, Gopal, for a very interesting talk. So if you have any questions, please unmute yourself and you can ask. Or if you have any problem with your microphone, you can also use chat box.
This is Amber. Can you hear me?
No, Amber, is that Amber?
Yes, yes. Can you hear me now?
Yeah, now we can hear.
First, I'm just curious, what are the time scales at which you are looking at these motions?
These are all different time scales. So for the pericyclic chemical reaction, the tunneling is around 1000 seconds, because this is carbon tunneling, and at least one organic letter paper tells me that this is kind of really fastest. One could comment on this one. I'm not the right person to talk about. The over the barrier reaction depends on the energy of your reactant. So the value that time you have chosen for the pulse, laser pulse, corresponds to around 23 femtosecond. For the diffusion process, it is 23 picosecond, something like that.
I see. So when you are doing
a little bit longer. Yeah.
So when you are calculating this, how are you accounting for, I mean, are you making the adiabatic approximation eventually?
Yeah, all are adiabatic, yes.
I see, I see.
Yeah.
Okay, thanks.
I have a question. This is Rajoshi.
Yes.
Well, yeah, coming back to your first work, this reaction.
Yes.
You had shown that the experiment shows that there are two paths, one via tunneling, one over the barrier. Now that should depend on the temperature at which you are performing the experiment.
Indeed,
So,
indeed.
Yes.
Yeah.
So if you increase the temperature, I would expect that over the barrier process will increase.
Over the barrier will be more dominant, but
More dominant. Yeah.
but there is a regime where you could have kind of dilemma, like suppose you are here somewhere.
Yes.
Right. So then you have a tunneling, and maybe you have over the barrier, and the temperature are almost like a nearby regime.
Yeah. So my question is kind of naive. I'm saying that you are doing zero temperature quantum mechanics essentially. I could see. You don't have temperature in your
Yes.
calculation.
Yes.
Now, is it possible that you introduce temperature, because maybe it is important here, and it is more important when you talk about diffusion. You showed me one slide where you talked about diffusion on a surface, on a solid surface.
And
there the phonon modes will be very important. I'm expecting here, yes, in surface diffusion.
So here
for sure you have to take care of temperature. Otherwise, I don't know.
So
experiment.
I don't remember what is the temperature here they have taken, because it's a recent work and first time I'm presenting. The work is under review. But in the case of semi-Bolovine, at least I could say definitely that whatever temperature, whatever temperature the reaction is taking place, the 0 Kelvin quantum chemistry and quantum dynamics is sufficient because the temperature is not enough to change the Fermi-Dirac distribution.
Yeah. But so you have a temperature. You have to have a temperature. In this case. Yes.
Here I don't remember. Here I don't remember whether the temperature, because it's the collaborative work where the diffraction part was done with my
Fermi-Dirac for the electron, but what about the motion of these atoms? I would expect these are like bosonic or something like that, because if you have a phonon bath, solid.
Here we are not considering this motion.
Okay.
Here the bond lengths are completely intact, so we do not consider any lattice dynamics here.
But if you consider, maybe that will affect your dynamics.
I mean, one could go to a more complex model, but we thought to make it simple, and first we have to
because the experiments are done at finite temperature, isn't it?
Yeah.
That's the way I asked the question. Okay, thank you very much. Thank you very much. Very nice talk. I really enjoyed.
Gopal, Sunoj.
Yes.
Um, So, is there an inherent restriction on the time scale of events that you can look at? Like both from the, I believe from the theory point of view, it may not be the case, but if you would like to compare with the experimental observation, do you have a kind of window that you are restricted to in terms of time scale of events?
So time scale, I would say there is no restriction these days. Because now people are able to go into 1 femtosecond. Even there are papers last year that people can generate even attosecond X-ray pulses. There are two kind of restrictions from the experimental point of view. One is that for these small molecules, the signal at the detector is very, very small, especially with these light atoms, because you know that X-ray diffraction scales with Z square. So people try to have heavy atoms in your system so that they can have a meaningful signal. And that is the, let's say the main purpose of these methods for the phase retrieval, those who do X-ray crystallography, multi-anomalous wavelength dispersion, MAD and whatever, this thing. Another technological problem is that controlling the delay between the pump and probe. Here, the pump and probe are coming from two different sources. So there could be some finite jitter or uncertainty between the two, and this is a main challenge. But people are overcoming over the years. So I believe in coming 5 years, so many XFELs are coming, and also people are improving the infrastructure of the existing XFELs, and much more things will come into reality. From theory point of view, there are a lot of things challenging. I mean, one thing I would like to mention that in hydrogen problem, one is the numerical problem was when we have done this coherent electronic motion. So suppose you create a coherent wave packet between the two states, A and B, and you would like to probe the dynamics of this wave packet. So it means that the pulse supposed to be smaller than the energy difference between the two. Then only you can probe different instances of the motion, right? So it means that when you have a smaller pulse, then you have a very, very broad bandwidth. It's the Heisenberg uncertainty principle between energy and time. So it means that it could cover several other electronic states. And then computing the transition among other electronic states is very, very difficult, especially with X-ray, where you cannot apply any more dipole kind of approximations, because the wavelength is almost like the size of your atom. And as you go higher and higher, your electronic states are getting denser and denser. So for example, for the benzene, we have included something like 7 or 8 excited electronic state with the KSSCF level. So these are the problems that we are facing, I mean, numerically.
So one small clarification in the you know, the last few slides that you have shown that benzene and the flux variations, right?
Yes, yes. Yes.
So I was wondering, like few years ago, few decades ago, people were interested in what is known as transition state spectroscopy.
Yes.
Yeah. So do you think that these are kind of a new version of old transition state spectroscopy, trying to look at events at the you know, the call or the peak of the surface?
Maybe I'm not aware about this transition state, but at least what I'm aware about this flux is that theoretically people used to calculate these fluxes, and most of the quantum chemistry packages give you this access. Even I know, at least I have seen 1 or 2 papers, for example, from Professor Pratim Chatras from Kharagpur. He also calculated these fluxes or current. Until date, it was more like a theoretical tool to understand or to have a better understanding of some processes. This is the paper where we have put into experimental point of view that indeed these quantities can be probed. That's what I could say only.
Okay. Thank you.
Any other questions? Okay, if not, let's thank Professor Dixit once again for wonderful talk and questions and answer session. And let me thank you all for joining today, and we will see you all in the next departmental webinar. Thank you.
Thank you. Thank you.
Right. Thank you, Gopal. See you.